Yeah. Uh, in the last class, we discussed the complex compounds, in which I told you regarding each and everything, like the definition of a complex, how the complex is being formed. It's a metal. It's a it's a dative bond between the metal and a ligand. Of course, ligand is going to donate its electron to the metal. Metals are going to have empty orbitals, so they will be gaining electron, and they will be forming a, I can say, a dative covalent bond, right? So today we are going to discuss the geometry of a complexes. Today we are going to discuss the geometry of a complexes, right? So geometry, it's an important topic. Geometry. Geometry of complexes. You know, we have two types of we have four types of geometries that we would be discussing. We can say that lost, lost means that the first one would be having linear geometry. It's gonna be linear. It's gonna be octahedral. Octahedral. It would be square planar, right? It would be square planar, and it's gonna be tetrahedral. So we will be discussing these four geometries. Okay, we would be discussing these. So starting from copper, I can say that copper, copper H2O6, copper H2O6. And of course, the charge on a complex is plus 2, right? The charge on a complex is plus 2. This is the formula of the copper H2O6. It's a hexa aqua copper 2, like the name of this complex, right? So the coordination number is 6. It means that there are 6 native bonds between the metal and a ligand, right? Or then also we can find out the oxidation number of copper by using the charge on a total complex, that is going to be plus 2. Since water is a neutral ligand, yeah, I was telling you, you must know the nature of a ligand, whether it's a negative, whether it's a neutral. You need to memorize it. Otherwise, you would not be able to do this one, trust me. You have to memorize this, right? So as I told you in the previous class. So now the thing is that what's the electronic configuration for copper? Copper is going to be, copper is 29. 29 means that I'm supposed to write argon, that is going to be 18, right? After 18, I can write 3D10 and 4S1. I told you this configuration in the previous class, right? So copper plus 2. So then I'm going to write copper plus 2. Again, I have told you this configuration in the last class, in the first class, I think. So when we were discussing is copper transition element or not? So copper plus 2 means, again, I'm going to write argon, that is 18. Then I can say that 2 electrons are lost, one from 4s and electron from 3d. Okay, so I can say that 4s is 0, right? 4s is 0. There is no electron in this one. After 4s, I have 4p. After 4s, I can share my screen. Wait, I'm going to share my screen. After 4s, I have 4p, right? Like that. This is 4s, this is 4p, and then I have 4d. And then what? I have 4d. 1, 2, 3, Four, one, two, three, four, five. Oh my God, why the screen is okay? So, how many water molecule I have? How many water molecule I have in this complex? So we have six water molecule. And water molecule means that it has a lone pair of electron on oxygen. So we have six. It's one, then I have two, then I have three, then I have four, then I have five, then I have six. Okay. Then I have what? Then I have six. Right. So uh, this lone pair would be donating to this 4s orbital and to this one, to this one, to this one, to this one, to this one. Okay, to this one. By the way, it's a ground state. By the way, it's a ground state. So what's the hybridization? What's the hybridization? How many orbitals are mixed? S, 3p, and D2. So the hybridization is sp3d2. So the hybridization is what? sp3d2, right? Or I can say that how many lone pair I have? There is no lone pair. There is no lone pair. Single. I have I have six bond pairs but zero lone pair. If you can see this one, I'm going to do this as well. Copper, copper, then six molecules of water around this copper like that. Okay, like that. So I can say this is H2O, 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 this is H2O. So we have six lone pair. Sorry, we have six bond pairs. One, two, three, four, five, six. On a central element, there is no lone pair of electron. On the central element, we have no lone pair of electron. So I can say that I have six bond pairs and zero lone pair. Whenever you have six bond pairs and zero lone pair, so what would be the geometry? Would be the geometry. I can say that it's gonna be octahedral. I can say that it's gonna be octahedral. It's from AS as well. When we were discussing the chemical bonding, in that we have discussed valence shell electron pair repulsion theory. What was that theory? On the basis of the presence of the lone pairs and a bond pair of electron, determine we can determine the shape of a molecule. So the same goes over there. So the same goes over there. So that's why I can say that the shape is octahedral. Okay, on the basis of lone pair and bond pair, I have decided. And also, this is very important. The hybridization is very important. Okay, I can draw the 3D structure as well. I can draw the 3D structure as well. I'm going to cut it down. Now I'm going to paste it over there. So basically, when I would be drawing the geometry of this one, so so I can say that it's gonna be it's called wedge and hashed line structure. It's not new for you. You are already familiar with this structure right away because you did in your AS as well. So just I'm going to share with. Don't worry about that. I think it today is a network problem. Okay. So it should be it should be like that. This is a dotted line. Okay. It's a 3D structure, right? So this is all about this one complex. It's a copper H2O6. So whenever you will see any of the compound, so you have to do the same thing. You have to do the same thing, right? Or what's the bond angle? What's the bond angle? What's the bond angle? It's gonna be 90 degrees. It's gonna be 90 degrees, you know. So I can say that since I have to write down the overall charge as well, since I have to write down the overall charge as well, so it's going to be plus 2 over there. Okay, it's going to be plus 2, and between each and every water molecule, the bond angle is 90 degrees. The bond angle is 90 degrees. Okay, so now um I can say, let's say I'm going to give you another one. Let's say I'm going to give you another one. Okay, okay. Let's say this is uh, copper chloride. So what do you think about that? What do you think about that? Copper CuCl4 CuCl4 2 minus CuCl4 2 minus. What do you think about that? So I'm going to give you the hint. I'm going to give you the hint. What you have to do, you have to first write down the electronic configuration of copper. And since we know that in this compound, in this complex, again, I have the same criteria. I mean to say that copper is plus 2. So the configuration would be the same. But now you need to know that in the previous question, I had six ligands. But in this question, I would be having 4 ligands. In this question, I would be having 4 ligands. So this is very important to know. So uh, then I can say that if I'm going to write this configuration of copper, that's going to be the same. I'm going to copy paste this because this is almost same. Okay. Yes. Then I'm going to just paste it over there. After pasting this one, we know that copper is plus 2. Yes, each and everything would be the same. Okay. But there would be a minute difference like that. It's gonna be 4 as 0. Everything is same. But I have one chlorine, another chlorine, another chlorine, another chlorine. Okay, all are having negative charge, negative charge, negative charge, negative charge. It's going to form just like that. Okay, so what's the hybridization? So what's the hybridization? I can say that hybridization is gonna be S and P3. S and P3, isn't it? I haven't used D. In the previous example, I was using D. So that's why the hybridization was sp3d2. But right now, I am only consuming the 2 orbitals, that is S and P. That is what? That is S&P, by the way, right? So, uh, so if the hybridization is sp3, so how many bond pairs and lone pairs are there? Right. So how many bond pairs and lone pairs are there? I can say that I can't see any lone pair of electron in this one. I can't see anything. So, uh, I can say 4 bond pairs and 0 lone pair. So the geometry would be, so the geometry would be tetrahedral. So the geometry would be tetrahedral, and the bond angle would be, and the bond angle would be 109.5 degrees because it's tetrahedral. Because it's tetrahedral, right? Okay. So what's the shape? What's the geometry? What's the structure that am I supposed to write? Like copper one. So I can say that it's gonna be copper. It's gonna be copper. right? And I have four chlorine atoms like that. Okay, so I can draw the 3D structure like that. You are already familiar with this structure, hopefully. Oh, uh, uh, one more chlorine. Then I'm supposed to write down the overall charge. The overall charge, okay. So it's going to be 2 minus, right? Oh, 2 minus, 2 minus. Okay, that's the geometry of copper chloride for 2 minus. So what's the hint for this? Whenever you will be getting any of the question, any of the compounds, so what you have to do first, you have to find out the I can say electronic configuration of that particular metal, and then you can see how many ligands you have. Then you can see the hybridization. Then you can see the total number of bond pairs and then lone pairs. Then you can find out the geometry of that particular complex compound. Now let's try the another one. Let's try the another one. That is, now you can try by yourself, then I would be solving it. Okay, you can check your concept. Uh, okay. Let's say, what do you think about chromium? Yeah, or I can say that this one, Ag, AgNH32. What do you think about it? Try yourself, then I'm going to tell you. It's very easy. It's really easy. Okay. Um, Now what am I'm going to do? What's the electronic configuration of silver? Of course, this compound is going to have. Uh, Now we have to think that what would be the charge on silver? We have to think about that. What would be the charge on silver? So that I can find out the electronic configuration in a more easier manner, right? So this is the overall charge, that is plus. So NH3 is a neutral ligand. There is no charge. So means that silver is going to have a +1 charge. Silver is going to have a +1 charge, right? Silver is going to have a +1 charge. So now, first of all, I'm going to write down the normal configuration of silver. That is going to be this one. You can focus on this. This is going to be the normal configuration. 1s2, or I can write down argon. It's a short one. Argon is 18. Okay. Then I'm supposed to write 3d10, 4s2, then 4p6, then 4d10, and then 5s1. We can write down krypton as well. Krypton is 36. So 18 plus 10, that is going to be 28. Then 28 plus 2 is 30. 30 and 36 is 38. So I can also write this configuration as a krypton. It's going to be krypton. That is 36. So this would be the electronic configuration for silver. Then what can I write for the silver? So it's going to be 4D10 and 5S0. Hopefully you are getting this, what I'm saying. So after the 5S, how many NH3 I'm going to have? So I can do that. I'm going to have, I can say school is school, public is school, public is school, down, public is school, right? If you remember that one table when we were drawing in the first class. So by the way, overall, I can say silver, the formula for the structure for Ag is going to be this one, AgN3 and then AgNH3, right? It's going to be like that. So it has two bond pairs and zero lone pair. So the geometry is linear. So the geometry is linear and the bond angle is 180 degrees, by the way. This is the shape of AgNH3 and then 2. AgNH3 and then 2. Okay. Um, then I can say you can try another one. You can try another one, let's say PtCl4 2 minus. What do you think about this structure? PT platinum, platinum, PtCl4 2 minus. Yes. You can write down the electronic configuration first, then I'm going to tell you. I'm going to give you 1 minute. Okay, so first of all, um, what's the electronic configuration for uh, platinum? What's the electronic configuration for platinum? Okay, platinum is number for platinum is quite higher. Even I can say that its configuration uh, is gonna be um, it's a xenon first, it's a xenon first, right? Then I can write 4F14, 5D9, and then 5,6S1. Should be more stable. Of course, it should be what? It should be like more stable. So I can say that it's gonna be, you can make it stable. You can make it stable after donating electron. It's gonna be 5D8, then 5S2. Sorry, 6S2. 6S2. Okay. So then I can say d orbital I have, that's going to be 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8. Or I can say even it's already stable, so I'm not supposed to make it stable because it was half filled. I just saw it is already half filled. I'm not supposed to shift any electron. It's already half filled, right? So after donating, it would be full filled. So like half and full both are stable. So now the thing is that I can write down the number of electrons 1, 2, 3, 4, 5, 6, 7, 8, 9. So I can do 9, this one, and then S1, right? This is going to be S1 state. It's a ground state. How many chlorine I have? Oh, by the way, after 6s, how many orbital I am going to have? Let me write it down. Let me write it down. I have 6p. I have 6p, 6s. Then I have 6p, and then I have 6d. 1, 2, 3, 4, 5. I have 6d. So how many chlorine I had? 1, 2, 3, and then 4. 1, 2, 3, and then 4. Okay, 1, 2, 3, and then 4. Right. So, what would be the hybridization? What would be the hybridization? I'm going to, this is in the ground state. I'm going to make it in the excited state. So now you know what I would be doing for that one. You know what I would be doing for like that one. So we have 4 chlorine atoms. So one chlorine would be going over there, another one would be in this, another one would be in this, another one would be in this. So I can say that it's gonna be hybridization would be DSP2, DSP2. DSP2, DSP2, DSP2. When the hybridization is DSP2, remember it's not tetrahedral, it's a square planar. If you remember when I was telling you this one, it's also the coordination number is 4. And for this one also the coordination number is 4. It's quite interesting. It's quite interesting, remember. It's quite interesting. When the coordination number is 4, so there are two possibilities. It may be tetrahedral, it may be square planar. I'm again saying it's a contradictory topic. So, but nothing about that. You can make it easier after knowing the electronic configuration, and then you have to see what the hybridization is. If the hybridization is, if the hybridization is what I can say sp3, it would be tetrahedral. It would be tetrahedral. It would be tetrahedral. And if the hybridization is dsp2, so it would be square planar. It would be square planar, right? So, so nothing to worry. This one, everything is easy, right? So, yep, it's a square planar. And when the something is a square planar, so I can say that, and so the bond angle would be, so the bond angle would be 90 degrees. So the bond angle would be 90 degrees. So from now onwards, when I would be giving you any of the compound and I would be asking the geometry, then what do you have to do? You have to write down the electronic configuration, then you have to see the hybridization. Then you have to see the bond angle, then you have to see the bond pairs and lone pairs. And by the way, how many lone pairs and bond pairs it has? Four bond pairs and zero lone pair. In the same way, when we were solving this one, I did the same thing. Four bond pairs and zero lone pair. Everything is the same. There is a confusion. There is a confusion when everything is the same. Why the geometry is different? It's all about the hybridization. If the hybridization is sp3, so it would be tetrahedral. And if the hybridization is a square planar, sorry, a dsp2, so the geometry would be a square planar. I would be asking this question in the coming classes so that it might be fixed in your mind that when we would be writing tetrahedral and when we would be writing like I can say square planar. Okay, got it? Hopefully you did. You got it? And if you have any query related to this, feel free to ask. You have to do some sort of past papers. You will see an idea. You will get an idea what's going on in this, how the examiner asks these type of questions, right? Okay.